If a city gets their water from groundwater, odds are they have a well field or they have several wells across the city that provide that. So we know that we pump a well, the water draws down. What happens when you have more than one of them? If those cones of depression intersect, then they're both affecting each other. They're affecting monitoring wells. So we're going to talk a little bit about what happens with multiple wells. Actually, it's quite simple. We just add the drawdown of the two of them. So if I have a well here and it's pumping, it has drawdown. Well, it has a drawdown at a certain point of S1. We'll put there using the little s for drawdown again. And if we have another well that affects it, this one in this picture, it's a little closer even. So we have drawdown S2. The drawdown at the observation well just equals both of them added up. And so the head at observation well would just be the initial head minus the combined drawdown. So we'll do an example here. I have a couple examples. These are from a previous homework. I'm actually not going to give you a homework assignment on this or have it on the exam. The assessment for this section is you're going to turn in a scan of the last page of the notes. Let me zoom out a little bit here. We have two pumping wells. They're 500 feet apart. We have the data on the aquifer there. The upper confining layer is at 670 feet and the lower one at 590. So we have 80 feet of aquifer thickness, and we're going to say the initial head is at 1080 or 470 above the bottom one. So we're going to use the bottom confining layer as the datum. So we're going to pump these. We pump at two different rates, and we want to know what the drawdown is after 7 days, and then the combined drawdown at monitoring well A. Well, we know how to do the drawdown. I'll show you the calculations in a second, but just in general, we're going to draw down pumping well 1, and then it's going to draw down from there, have a cone of depression. So I might draw it like that. And then it's symmetrical, right? And then I have another well that's pumping. And pumping well 1 is at 400 gallons per minute. Pumping well 2 is at 150 gallons per minute in the same aquifer. So it's not going to draw down as much. Maybe put it there. So what we do is we take, for like this monitoring well here, we take the drawdown from monitoring well 1, from pumping well 1 rather. Then we add to that the drawdown from pumping well 2. And so the result is there. So if we do that there, this one's barely affecting there and this one there. So then after the two wells, we have the combined. It looks kind of like that. I've given this problem as a homework before, and this is what the graph looks like. I have it graphed out. And I did calculate that. And if you look here in a spreadsheet, the W of U, I have that infinite series. And once you type it in there, you got it. It's not that hard to deal with. And so I did the drawdown for each of the pumping wells, and then I added them together and had the combined drawdown. Then I subtracted that from the initial head, and that's the head. And at monitoring well A, looks like that's 392 feet. So I'll put 392 feet here. Part B, it asks, will it draw down below the top of the aquifer? So if you draw it down below the top of the aquifer, the confined aquifer is no longer under pressure, so it's not really a confined aquifer anymore. So how can I figure that out? Well, I'll go to here, and I'll go over this way, and this is actually, if you look at the formula there, I took the minimum there. So the minimum is 318. That's above the bottom here. So I only needed above 80 for it to still be confined. So will it draw down below the top of the aquifer? No. 318 is greater than 80. What is the head monitoring well A after 60 days of pumping? So this was 7 days. What if this goes to 60 days? F9, we calculate 370. So this is 370. What about after a long time? After 60,000 days, gets down to 302. So it keeps going down, but it's still above the top of the aquifer. So again, what we did, we found the drawdown from well 1, then added the effect of well 2, and we get the combined effect. So that's what happens when we have two wells affecting each other. What if we have a couple other things that might happen? So we could have a no flow boundary. So it's drawing down and then it hits out here. And once it hits this boundary out here, now it can't draw, it wants to draw down out here, right? But it can't get any water out here, so it has to get more water out from here. So it draws down more at the boundary. So what we can do there is we can simulate it with an imaginary, I say, or just an image well. So I go from this radius here till I hit the boundary, then I go that radius again out there and I put a image well in there. And then I pump that at the same rate. And so we have from the real well, we have a drawdown from that. We have the same drawdown from the image well, and so we have a combined drawdown there. And it's still a little effect on the other side. Another thing that could happen is it hits a stream or a lake where it wants to draw down out here, but it doesn't need to or it can't because the water is coming in there. So this lake will hold the water level up there. So it does not have to draw down there. And we can simulate that by doing the same thing again. Our boundary, in this case, our boundary is water coming in. We put a image well on the other side, and then we pump into it. So it's not drawing down, it's drawing up or negative drawdown or something like that. So we would have this drawdown from the real well, and then we take this one, we're pumping in, so we have a draw up from that. And so the net effect is, so when this one gets out close to the well here, it has not much effect, but it has some effect, has more effect there. So in both these cases, we get an asymmetric drawdown. Another former homework problem here. We have a well, and then we have a boundary out here, and then we want to know what is the head at monitoring well 1. So we're pumping out of here. We hit this boundary at a radius of 200, right? X equals 200 up to X equals 400. And how do we simulate that? Well, we put in another one 200 feet out there. And then we have the drawdown from this one. And then we have the drawdown from this one, and then we add those drawdowns. All right, right at this point, it's twice that drawdown, but here it's like at monitoring L1, it's a lot from the pumping well and a little from the image well, so it's about there. It gets out here, it's just a little from the image well, so it's a little below what it was there. So it looks something like that. The combined effect. And I actually pasted in here below, you see on your page, the actual results of that. So it looks like that. That's from the calculation again. Here's the calculation, the same thing with the U and the W view. And then I plotted it up there. So I just copied and pasted that spreadsheet from that first one in here and changed the numbers, and we get the combined effect here. This doesn't exist over here. Let's just put in so we can do our calculation. And you can see an asymmetric drawdown. It's drawn down more toward the boundary. I had a third problem that I think I've only inflicted on the students one time, but I have a diagonal boundary there and I have the coordinates here. So we're doing it 2D, and I want to know the drawdown at monitoring well 1 and monitoring well 2. So to simulate that boundary, I go perpendicular to it, and then I go out there and I put the image well there. So again, I found the radius. I just put a formula in for each square, each cell in Excel. Find the radius of pump well and the image well, the drawdown using my formula. Well, that's the U, and then the W of U, and then the drawdown using the formula, and then the combined drawdown, and then the initial head minus the combined head. So that's a fun one. I won't inflict that on you. If you graph that, you get this. Again, this upper part doesn't exist, but you see here, you have, because of the boundary, you have an asymmetric drawdown with more drawdown toward the boundary. And then in this case, it's two-dimensional. This is the page I want you to scan and turn in as an assignment. So we have a pumping well here. It has a stream on one side and an impermeable barrier on the other side. It has two monitoring wells. So from the stream here, the way I simulate that is I take the same radius and I go from the front of it here, right? It doesn't know how wide it is. It gets water right there. So I go this R and I go the same distance on the other side. I'm just going to eyeball it. I could take that, and then I put in a pumping well where I pump in, and then on the other side I have an impermeable layer and I do the same permeable barrier and do the same thing. I go the same from this edge here, I go out there, and then I put in an image well and I pump out of there. So I have more water coming in here, so that will raise the water up here and lower it here. So this one on this side is going to be higher. And this one on this side is going to be lower. So this will lower monitoring well A down some, but it won't lower it down as much as it monitoring well B. Same thing up here. This will raise monitoring well B up, but not raise it up as much as monitoring well A. Right, so we have drawdown a well here, and this is what happens if nothing's affecting it. But then we put in this ditch where we have water there. So the head is going to rise to there. So how do I simulate this, and how do I calculate the head for the rest of it? Well, let me think. I'm going to put a image well from that boundary. I'm going to put it over on the other side here. So about here. And I'm going to pump into that thing. And I'm going to raise the water up. So this one, I got to raise it up from here up to there. So the water there needs to raise it 1, 2, 3, 4, 5 squares. 1, 2, 3, 4, 5 squares. So this one is probably going to be like above there somewhere. The same distance above there as this is below. And then if I look here, when I get out to here, there's a little bit of drawdown there. So I'll have a little bit of draw up here. So the combined effect will be a little bit raised up at the well and more raised up at the ditch. And so then this is the combined. So make yours a little neater than mine and hand in a scan of this page. So in summary, for multiple wells, we just add up to the drawdown and find the head that way. And then for a couple of kinds of boundaries, we can simulate that by putting in image wells and just doing a superposition of the image well effects with the real well effects. All right.